mightiest machines on the planet. Big, mean, invincible. Battling Mother Earth, the world we know couldn't exist without them. In this episode, we go deep underground, meeting the machines that are making mincemeat of the hardest rock on the planet. A multi-limbed Terminator that stabs through granite like it's butter.
We're talking about a big machine.
A stocky superhero that dwells closer to the center of the Earth than any other.
By the time you get down here, you're practically in tears from the pain.
And a fearsome monster with a voracious appetite and gnashes to match.
And this thing has a mind of its own.
It's time to get behind the wheels of some dirty great machines. Kidd Mine in Ontario, Canada is the deepest base metal mine in the world. It plunges nearly 2 miles straight down. They use a method of extracting the metals called blast hole mining. Without the most experienced miners using the best machines available, the dangers here would be overwhelming. A deposit of copper and zinc ore stretches vertically down for miles. A network of shafts and horizontal tunnels, Kidd Mine is 800 meters wide at the top, tapering down 3,000 meters. Vertical columns of the ore, called stopes, are excavated at several places at once. Up to 30,000 tons of ore can be excavated from just one stope using drill and blast. But with such big explosions, there's a risk of delaying production. Drilling supervisor James Peters has a unique understanding of how the mine works.
Picture this as a 10,000 foot tall tumbling block puzzle, which is essentially what our mine is. Now, let's consider these blocks as our stopes. So we have to start with the ITH drill, making a stope. So first we're going to take out just a little bit of it to make a void.
This void is then filled with cement to ensure stability.
Okay, we have to be cautious not to take too many stopes close together. If we take out too many blocks together, we're actually going to collapse the mine.
Fortunately, the extraction is carefully planned to make sure that never happens. For the next 11 hours, James is saying goodbye to daylight as he makes his way down to the bottom of the mine. A spiraling ramp 12.5 miles long will take him to the closest man has ever been to the center of the Earth.
Right now we're in the ramp at about 8,400 feet underground. We're just continuing down. We still got about 15 or 20 minutes of driving to get to the very bottom. It's the longest continuous ramp in the world. A trip from the surface to the bottom can take anywhere from 40 minutes to several hours, depending on the type of vehicle you're driving. I'd have to say I know the bottom of the mine like the back of my hand. Not too much further. This is it.
Yeah, no deeper here. This is it.
The mine has 200 people working underground at any one time, 24 hours a day.
I suppose every day the guys that come down here and work are kind of like Jules Verne in the journey to the center of the earth. Maybe someday we'll go a little further and we can actually see what's going on down there. I think we got a ways to go yet, though.
Working at such depths brings its own unique challenges.
There's phenomenal pressure, barometric pressure, and if you have any kind of cold or sinus problems and your ears won't unplug, by the time you get down here, you're practically in tears from the pain.
At the first sign of pain, miners are instructed to return to the surface. And life down here isn't easy for the machines either.
Trying to get equipment to work this far underground, you run into all kinds of problems. The temperature causes the oil to heat up, which causes the machine to overheat and shut down. It's hard just to get enough air for the diesel engines to run.
But undeterred by the difficult conditions, an amazing bit of kit is spearing through the hard rock. This is the in-the-hole drill, or ITH, 500,000 pounds of rock-busting technology. It can drill holes 15 centimeters wide and up to 175 meters deep, and at almost any angle desired.
Not only can it drill holes that are straight down, but it can turn and drill holes in a complete circle. And this mast, this drilling module, can turn 180 degrees straight up. It can turn almost 360 and go back to where it started from.
A new stope is being prepared. First, the ITH drill needs to create a ring of holes tens of meters deep. This allows the explosives, the blast bit of drill and blast, to be inserted deep into the rock face.
So you got the bit that goes into the hole and actually breaks the rock. You got the hammer, which makes the bit go up and down. And then you got the drill rod, which is what adds length to the hole. So all the work's being done by the hammer and the bit. The rods just continually make the hole longer.
For the ITH drill, hammering is every bit as important as rotation. It's the only way to smash through the hard rock.
The carbides actually chip away at the rock as it's turning. So that sound you're hearing, that hammering, that's that bit actually sliding up and down over and over again at a phenomenal rate. Now, what happens with the solid rock is it ends up looking like this, and it just absolutely pulverizes the ground. It just turns it into dust and pebbles. So the solid rock that we had turns into just powder, and that's the key of what we do.
The pulverized rock needs to be cleared from the hole, or the drill could get stuck and delay the operation. James's ITH drill is on the top of the stope. A ring of holes are drilled that penetrate the stope up to 40 meters to the bottom and 15 meters across. When they're filled with explosives and blasted, the rings break the ore into small lumps of rock that can then be collected by diggers at the bottom of the stope. Despite the difficulties of working so deep, progress on the stope is going well.
Chris has just loaded another rod on. Now he's going to continue to add rods on, and the hammer will go deeper and deeper in the hole, and it will stay in the hole. And it will always hammer at the very bottom of the hole.
The ITH drill needs careful and constant monitoring. James and his team rely on their years of experience to make sure everything goes to plan.
If you don't make a tight enough connection, you're going to lose air pressure, and you're possibly going to lose water. And there's a good potential that those rods will start bending in the hole. Most people don't realize it, but steel does bend.
And bent rods spell danger.
Your hole could end up being 10 feet away from where you expected it to be. And if we don't drill straight holes, they don't break the way they're meant to break.
A bad break means a real risk of slowing production. Miles beneath the surface of the Earth, James and his team are under huge pressure.
Gotta loosen off the head a bit.
At Kidd Mine in Canada, a dirty great machine called an in-the-hole or ITH drill is paving the way for a drill and blast operation nearly 1.5 miles below the surface. Drilling supervisor James Peters needs to trust his machine. This mine is so deep it's the closest humanity has traveled to the center of the Earth. So any mistakes down here can have a huge impact.
These holes are about 120 feet or 35 meters. That'd be about an average size for us. We usually go between a 30 meter and 40 meter hole.
To penetrate so deep, the ITH has a secret weapon: air. Very, very high pressurized air, 10 times that of a car tire. This air is shot down the drill rod to the hammer, making it oscillate back and forth at a phenomenal 2,000 times a second. The same air is also used to clean the holes, flushing the broken rock up to the top at over 120 miles per hour. Simultaneously, the drill rods rotate, pushing the bit and hammer forward, deeper into the hole.
Okay, so we're 6,900 feet underground. That's well over a mile. And the ground down here is under extreme pressure. So the rock's actually closing in on the holes. Before we get a chance to blast it, the holes are squeezing closed.
If the holes close up too much, the blast won't be big enough.
So it's probably hard to understand that those holes can actually squeeze because we're drilling in solid rock. But the rock's quite flexible and it can move quite a bit. It almost flows like water, but at a really, really slow rate. So these holes, in a matter of days, are actually moving enough that we're not, the 4.5 inch that we drilled it, they're not nearly that size anymore. They've shut down to maybe 1 inch or 2 inches thick.
James and his team have a matter of hours to complete the drilling before Mother Earth starts to close up the holes.
Okay, so we just finished ring 1, and these are all clean now. Everything's good on this ring.
Hole 4 and hole 5 are still.
So you're gonna move on to these.
Yeah.
Okay, so that's ring 1, and ring 2's good.
Ring 2's complete.
Okay, and ring 3 is complete. Okay, so we're gonna move into these other holes, and we're gonna clean these 2 here. And after that, you're gonna recheck them, make sure they're all good. Okay.
It's taken 6 days to drill the holes necessary for a successful blast. After a final back-breaking 10.5-hour shift, it's time for James and his team to head back to the surface. Once the explosives have been inserted, an almighty blast will smash thousands of tons of rock. But imagine doing the same thing beneath a city. In Helsinki, Finland, a new metro line is needed to cope with the growing population. But the city is built on the hardest rock known to man, granite. The only way to dig a metro tunnel through the granite is by drill and blast. But getting it wrong threatens the lives of not only the workers below ground, but the thriving city above it. It calls for a dirty great machine to drill with surgical precision. Called a tunneling jumbo, it looks like a prop from a sci-fi movie and features some of the most advanced drilling technology on the planet. The tunneling jumbos are drilling a 35-kilometer extension to Helsinki's metro. Once the holes are drilled, explosives are inserted to blow apart the granite. But the biggest challenge is that the metro line runs just meters under residential areas. So each blast has to be the precise shape and size to prevent the buildings above collapsing in.
When you're working in urban areas, you always have to consider the people living here. Vibration levels cannot be too high, so the buildings could collapse or something like that.
And fortunately for Helsinki, this Hardrock Hero is manufactured just 200 miles north of the city.
The overall weight of this machine is almost 50,000 kilograms. The height of the machine in working conditions is about 4 meters, so we're talking about a big machine.
Jussi Pura is the product manager in charge of the tunneling jumbos. Today, he is conducting final tests on a brand new machine.
Right now we are standing right next to the actual rock drill, and this is the heart and soul of the machine. All the rest of the machine is here to support this component. And this is the component that actually breaks the rock.
But the tunneling jumbo doesn't just have one drill, it has 3, all attached to boom arms that triple the work rate of the machine.
The boom of the machine has 8 joints. These joints allow the boom to be maneuvered into any position that the operator wants.
This jumbo is so advanced it doesn't actually need a human operator. It's more than a machine, it's a robot.
I think that the coolest thing about this machine is the automation. The fact that we can have one guy operating the machine or just watching the machine while it positions the booms automatically and drills automatically. I think that's great.
It weighs 44 tons, heavier than 6 African bull elephants. With a maximum drilling length of over 6 meters, it could punch a hole straight through the thickest walls of the Tower of London. The drill rotates at 400 RPM, 12 times faster than old-school vinyl. And it costs £1.7 million, bigger than a banker's bonus. Before this newborn robotic tunneler leaves the factory, Jussi has to calibrate the boom arms perfectly, or his client could make some very dangerous mistakes out in the field.
When the structure is shorter, it's stiff and quite accurate. But then when we extend it, it starts to bend under its own weight.
Saggy booms mean inaccurate drilling. Jussi needs to find out the exact extent of the bend.
So when the boom is in this position, its length is 10 meters. We mark the position of the boom with this white tape here. As we start moving the boom forward, it also starts to bend. Originally the boom was here on this white mark, and now we are 30 centimeters lower. And this is an error that we have to correct.
For this Hardrock Hero, precision is everything. So a surveying machine corrects the jumbo's onboard computer.
As we can see here from the screen, when the boom extension is 1 meter, we have some bending, 2 meters, a bit more bending, and we have the entire behavior of the boom recorded. So even though the booms are so heavy and the coverage area is so big, once this machine is calibrated, we can position the drill bit with an accuracy of less than 5 centimeters.
With the boom arms calibrated, it's time for the tunneling jumbo to clear one last hurdle. Built on granite, the factory is the only one in the world to have their very own mine to test their machines.
We know that the booms are accurate, we know that the machine works, now we want to see that the drilling works also.
The test wall has been drilled so many times by previous jumbos, it resembles a giant pincushion. Now, each of the boom arms on this new machine gets their own chance to eat rock. With the test team inspecting the holes, Jussi can deliver his verdict.
This machine seems to be working quite well. There are some minor problems in the hydraulics, but we'll fix them before the machine leaves.
Such meticulous testing is vital. Because in Helsinki, the tunneling jumbo is excavating a new metro tunnel just a few meters below the city center. The jumbo needs to create 100 holes within a precise pattern called a drill plan. The holes are 6 meters deep, and if the blasting goes to plan, the tunneling can advance another 6 meters further forward.
When you're dealing with rock and you don't know exactly what lies ahead, it's always a challenge. You cannot plan everything, so you just deal with the problems. That's why it's really important to have reliable equipment like this drill rig. This one needs to work perfectly.
In recent weeks, the tunnelers have hit problems. The granite in this area is harder than they'd anticipated, and progress has slowed.
Depending on the difficulties that we might have here, the advance is different every week. We normally advance around 50 meters per week. The target is actually 60, so we're a bit behind, but we're hoping the rock might change.
Today they're in luck. The 100 holes have been drilled perfectly in under 2 hours. It's time to back the multi-million-pound machine out of harm's way, load the holes with 600 kilograms of explosives, and stand well back. Thousands of tons of Finland's nemesis, granite, is now scooped up and removed from the tunnel. By 2015, this will be a brand new metro line, transporting Helsinki citizens to their destinations. All thanks to a wonder of engineering, the tunneling jumbo. But drill and blast isn't the only way to get large chunks of hard rock out of the ground quickly. There's a monstrous alternative much closer to home.
We could make areas of Cheshire collapse if we weren't conscientious about what we do.
The rolling Cheshire countryside. A picture of rural tranquility. But 200 meters underground lurks a mechanical monster. The continuous miner. It's a rock-munching beast with one mission: eating salt. Millions of tons of it. A thick horizontal layer of rock salt has been mined here since 1844. Now 8 square miles in area, Winsford Mine is the UK's premier source. What's mined here ends up on Britain's roads during big winter freezes. Up until 2002, miners used drill and blast to excavate the salt. But this hazardous method was replaced by just 2 continuous miners, tasked with producing 6,000 tons of rock salt every day. Or come winter, the country will grind to a halt. The man who keeps these monsters munching is Gordon Dunn.
Well, the continuous miner is a heavy-duty machine and it's built for this type of environment. There are a lot of these machines in this type of salts and potashes and those materials, and they are built to last.
The business end of a continuous miner is a revolving drum that rips salt to pieces. Loading arms force the salty chunks down the machine's gullet. These pass through the machine and are excreted onto a conveyor that takes them to a crushing plant.
The continuous miner has made things better by giving a roof area that's clean and stable. Whereas when you drill and blast, you can sometimes have small bits of rock that drop out. You have to send people up to the roof to check scale it. We don't have to do any of that with a continuous miner. It's more productive, it gives a cleaner finish, and with it giving a cleaner finish, it's safer.
The machine is a similar size to a coach lying on its side, but it weighs in at an impressive 120 tons, equivalent to just over 2 battle tanks. Working at full speed, it swallows 2,400 tons of salt every hour, enough to fill 130 wheelie bins a minute. And it costs a whopping £2.5 million. The continuous miner isn't controlled by a driver sitting in a cab. It's one of the world's largest remote-controlled vehicles. Via a handheld control unit, an operator moves the miner into the rock face and raises the cutting head through the salt.
The cutting head spins continuously and it's pushed forward with the tracks of the machine, pushes it into the rock, and the tungsten carbide pick cut the rock off and it ranges up and down, cutting the rock and bringing it down onto the floor. This is the first cut the machine's made into solid rock. The machine can cut 4.5 metres high and it cuts 4.2 metres wide. And then it drives until it buries itself in the rock and it's all the way in 10 metres, and that's what you can see here. When it's done that, it comes out and does the same next door.
The result is a labyrinth of interconnected caverns branching out under the Cheshire landscape. To prevent the countryside above from falling into the mine, Gordon employs a tried and tested strategy called room and pillar.
We could make areas of Cheshire collapse if we weren't conscientious about what we do, but we don't behave like that. We currently mine 75% of the salt that's in this area and leave 25% up as a pillar. So you calculate how much support you need to make sure that the roof never moves. And it's very important to us that we don't move the roof and cause any subsidence in this area.
A steady supply of rock is passing through Winsford's crushing plant. Here, large salty chunks from the rock face are slimmed down into grit ready for spreading on Britain's icy roads.
When the rock comes from the continuous miner, it can be up to house brick size and even bigger. So we have to crush it down to get it down to a size that is easily spreadable on the road and not too big, because if it's too big when it goes on the roads, it can damage people's windscreen. And then what happens is it goes through a screening process that goes through these meshes, and anything that can fall through the mesh is then product that we sell. Anything that's too big to fall through the mesh will then move on and go to the next crusher and be crushed down to a size that can go through the mesh.
Gordon monitors the continuous miner's output. At this rate, the machine's on course for meeting this shift's rock salt quota. But there's a problem. Chomping through 500 tons of rock salt an hour has played havoc with the continuous miner's teeth. They must be replaced fast or the machine slips behind schedule and won't make the quota. It's a job for the miner's dentist, Chris Blaine.
These are called picks. These will actually chip away at the rock. And that one's one that the point's worn away. And you can see these are very hot. And that sort of starts to go black as the metal fatigue sets in. Eventually, they just snap off. If we get one or two of these that are broken off, then instead of getting little pieces, we'll get big slabs of rock, which block everything up, cause chaos.
With such a large appetite, the miner's teeth need changing constantly every 8-hour shift.
Within a week, the whole lot would have been replaced, some more than once.
With 120 picks on each machine, the annual bill for replacing them is a massive £75,000 a year.
That one there's broken, Tom. Take it back a little bit more and I can get to it.
With new dentures fitted, one of Winford's 2 continuous miners is ready for its next course. By the end of the shift, the continuous miner's eaten through a staggering 2,000 tons of rock salt and met its quota. Like most subterranean machines, the continuous miner at Winsford will live its entire life underground. But Winsford Mine doesn't have an access ramp for vehicles. All men and machines, including ones the size of a continuous miner, have only one option: lift shafts that plunge 200 meters straight down.
We're at the bottom of 4 shaft here now. This is the cage that we transport all the materials and equipment into the mine.
It's like getting a ship into a bottle. Luckily, the engineers at the continuous miner's birthplace have been doing this for decades. Over the last few months, a brand new machine has been painstakingly built and tested at the factory in Franklin, Pennsylvania. It's destined for a mine in Laos, Southeast Asia. Like Winsford Mine, it has a small access shaft, and the miner can't go down in one piece. All the work that went into making this monster machine now goes into reverse in a process the engineers call the teardown.
I think it's kind of neat because, you know, I got to walk it all the way through being built and walk it all the way from being torn back down. So it's kind of neat to see that, yeah, we can put it together, but we can also break it back apart. It's like a puzzle. When we were designing it, we ended up making a square that represented the mine shaft, and every piece had to be passed through that square to make sure it worked. And that was our catch-all to make sure that we didn't assemble something on the floor that couldn't be broken down into its smallest particle and pass through that.
Right there is what's first, the ripper thing. Yeah, what's next?
John Halberg and his team must disassemble this 150-ton continuous miner into 10 components and 35 small boxes for shipment.
It is a bit weird to have to tear that machine down after we get it all built up, but it's one of those constraints that we have to live with, that once we get it constructed, they can't just take it down in the mine in one piece, so it's just something you have to learn to live with. Typical teardown is usually about a day or 2, but given the machine that you're looking at probably a 3 to 4 day teardown.
With the clients breathing down their necks, the pressure's on to get it done in time.
That's the customers here and everything, they're checking it out. And as we tear it down, they get to see what's going on and what all's involved. Sometimes they get in the way, sometimes they don't. No problem, no.
We shouldn't be raising this up anyhow.
No. The only thing we have to come is high enough to be off the floor to hook up when we pull the bolts. You get high enough to get the bolts out.
Right.
That's all higher we have.
The first piece to come off is the ripper chain. Under high tension, removing it is the riskiest part of the operation.
It's the most dangerous part of the carrier. You want that idler because you don't know where it's going. And this thing has a mind of its own. It's ugly fast. So that's what I mean. This is probably the worst part of the whole tear down.
Now it can come apart with no problem. Just a matter of unbolting stuff and taking it apart. That part there, once you unpin it, it could swing out, it could do whatever, so we were trying to get that done right away.
Over the next 3 days, the continuous miner slowly dissolves into smaller and smaller parts. And is packed into boxes. Soon, another hero of hard rock will be ready for action.
It's neat that a machine that big can be used underground and it's under your feet and you don't even know it. The fact that it could be mining right now and you would have no idea that it's going on underneath you.
At Kidd Copper and Zinc Mine, something rather more explosive is about to happen under the earth. Using the blast hole method to excavate the ore, in just a few hours, a massive explosion will clear away a new area of the mine and bring thousands of tons of rock crashing down.
As long as the powder goes off properly and all the caps are set right, should be no problems here. It's going to be wonderful.
Kidd Mine, Canada. A dirty great machine called an in-the-hole drill has done the hard yards on a new seam of copper and zinc ore called a stope. It's the first part of a technique called blast hole mining. The drill creates a ring of holes that are filled with explosives and blasted. The ring breaks the rock downwards, creating up to 30,000 tons of copper and zinc ore that can then be collected by diggers at the bottom of the stope. Drilling supervisor James Peters is Lord of the Rings.
3 rings drilled here, and the sequence of blasting is going to be the first ring closest to our slot, then the next ring, the ground will break towards this one, and then there's a third ring even further back that's going to blast in, and then when it's done, all 3 rings are going to be blasted into this area. We have a slot that's already there as a void, so it has an area for the muck to break into, and that's a perfect situation to have a nice stope break. As long as the powder goes off properly and all the caps are set right, should be no problems here. It's going to be wonderful.
After drilling, the blast boys took over and inserted explosives deep into the holes. Today is D-Day. D for detonation.
Okay, so what we have here is the blast ring that we're ready to let fire. We saw the drill drilling here. Now it's loaded with emulsion. And emulsion is an explosive that kind of has the consistency of toothpaste. This is it right here. It's a little dirty with some muck in it, little cuttings, but you can see it's just a real pasty, funny feeling stuff, kind of like peanut butter or toothpaste, really, really thick. And all the holes are filled with that. There's about 4,500 kilograms of explosives in these holes right now.
The blast will be the equivalent of 4.2 tons of TNT, nearly 1.5 miles below the surface of the Earth. James needs to make sure everything has gone to plan.
It's going to be quite a nice blast. It looks really nice. The guys have done a fantastic job. Everything's tied in on these are the detonating caps. So they tie into a lead wire that sends a signal, and it sends a signal down each hole. And in each hole, there's two caps. So in case one doesn't go off, you've got a second cap to as a backup. So if the first one doesn't fire, you got a backup, because the last thing you want to do is have the holes not firing, and it's a real waste of time. We have to come back in, clean all the holes again, reload them, and try a second time. So it's best to get it right in the first try.
Being miles underground and surrounded by explosives, most people would be shaking in their boots, but not seasoned pro James. In the control room, the blast operator is making his final checks.
First thing we're doing here is calibrating. And then the next step is programming.
This blast line will receive a signal from surface that's going to tell it that you're fine to blast.
Okay, we got communication.
And each one of these caps gets that signal and says, okay, I'm going next.
James and the blast op are happy. It's time to leave.
Okay, you're almost done.
There's all kinds of safeguards in place. They make sure that there's nobody underground, because this is going to really shake the mine. And if someone were underground, it could, there's a chance that they could get hurt. Obviously, it's a lot of concussive force here, but there's also a lot of noise, there's a lot of dust, and there's a lot of fumes. So you don't want anyone anywhere near the area when this goes off. So what's behind me here is the tag board. It's the tagging system for the underground. Everyone's got a tag just like this, and it's got their picture and their name. So each guy tags in, and then we know that he's underground. Once it's clear like this, we know that they're not underground, and we can go ahead and fire off our blast at that point.
The tag board is empty. James signs out, his job done. Modern technology means no plunger or detonation button. It's all done remotely. Everything comes down to a single click of the mouse.
Yeah, looks good. Got a good connection. Hey, we're ready to roll, rock and roll. Fire in a hole. Yes, sir. Blast is fired. Can you hear it?
Yeah, I feel that.
The blast was so massive, it actually triggered some seismic activity in the mine. A mini man-made earthquake.
And we got something here, so that tells me that there was some seismic and a blast.
There was a hit here on the intersection too, so.
65. That was a seismic and a blast.
Well, it was triggered by though.
It went off. Oh, good. That's,
So now we're just gonna have to wait and see if they're gonna shut the level down because of the seismic at the intersection.
Looks good.
It was one mighty explosion, but it's safe to return. James now needs to go to the bottom of the stope to see whether it meets his approval.
Good size? That's a great size. That's ideal. So for blasted muck, this is a really nice size. It's very easy to work with. The rest of the process is going to have a really great time with this. We blasted like this, we did our job right.
It's thanks to the in-the-hole drill that the operation was a success. With pinpoint accuracy and working under extreme pressure, James Peters and the workers at Kidd Mine can continue to supply the world with the metals we need. The Hardrock Heroes. 3 mighty machines smashing their way through the planet's toughest rock for our benefit. Thank you, dirty great machines.